Right, so this is going to be our last chapter, which we are going to talk about asynchronous sequential design. Now, in synchronous sequential circuits that we have seen in chapter 5, the change of internal state occurs in response to the synchronized clock pulses. And asynchronous, which means it's not using any clock pulses over here, they do not use clock pulses. The change of internal state occurs when there's a change in the input variables, like the combinational circuits. And in synchronous sequential circuits, we have seen that there are memory elements, which we call the clock memory elements, flip-flops. But in asynchronous sequential circuits, we either have a unclocked flip-flops or time delay elements. And the memory capability of these time delay devices depends on the finite amount of time it takes for the signal to propagate through the digital gates. So asynchronous designs, they are harder to design because they might have some potential instability issues that I have mentioned in the last chapter. So the timing problems can be involved with the feedback paths that we incorporate in it. And the change of the state occurs immediately after input changes. So as we don't have the clock, we cannot actually control when the data is going to be entered into the system and when it is going to leave. So care must be taken to ensure that each new state keeps the circuit in a stable condition, even though feedback path exists. Okay, so let's see the differences. The synchronous sequential circuit, change of internal state in response to synchronized clock. Clock flip-flops latches stores the states, easier to design since the change of state only happens in small interval time. And asynchronous, change of internal state in response to change in one or more of the inputs. Unclocked flip-flop latches or time delay elements like combinational circuits with feedback stores the states. And they are harder to design because of the potential instability issues, and the change of state might occur immediately after it. So now, when we think about asynchronous sequential circuits, they are reusable in various applications. So when the speed of the operation is important, especially in those cases where the digital system must respond quickly without having to wait for a clock pulse, or they might be useful in an economical way because they are small independent systems, so you don't need to have a clock generators like clock signals going all around your circuits. And also two synchronous circuits with independent clocks needs also communicate with each other, so that's also a problem that we'll be facing. Okay, so when we talk about asynchronous sequential circuits, a typical system block diagram is something like this, where we have got set of inputs, x1, x2, set of outputs, z1, z2. This is actually, again, a combinational logic. Now, the difference between combinational logic and the synchronous sequential logic with these is that we can have a number of outputs over here. We can say Zn and n number of inputs. So that fits in. The feedback. So we can have the feedback and we can have some delay element. So it can be a wire, it can be something that will feed back in to the logic. Okay, so we can say that time delay element over here that can be expanded so that we can have multiple of those. That fits back into the combinational circuits. Okay, so no clock is used over here. The memory elements that we have got, they are delay elements, and it's like a short-term memory for a sequential circuit, actually. So in a gate-type circuit, the propagation delay that exists in the combinational logic circuit paths, which we have seen it, from input to the output provides sufficient delay along the feedback loop so that no specific delay elements are actually inserted into the feedback path. So we can assume that this is just a combinational circuit and there's a feedback path. So that's actually giving us enough time from the propagation that we can consider it. And they're not explicit, they're intrinsic to the combinational logic, and we can have a given number of input variables, and we can have circuit stable if the present state and the next state. So we can say the outputs over here. So let's say y1, this is yk. They are capitals, and their next states, the present states, are small y1, capital yk. Sorry, small yk for the present states. Okay, so this is how we can represent the present states and the next states. And important is this small y1 must be equals to capital Y1, so to have stable states. And in more generalized form, small yk might be equals to capital Yk. Okay, so in both cases, to have a stable state, the present state must match to the next state, or next state must match to the present state. Right, so in order to make sure that a proper operation of the asynchronous circuits, we must allow to attain a stable state before the input is changed to a new value. So we have to make it wait to match the present state to the next state, and then we can change the value. Because of the delays in the wires and the gate circuits, it's impossible to have two or more input variables change at exactly the same time without an uncertainty as to which one changes first. So therefore, let's say the simultaneous changes of two or more variables are usually prohibited. What do we mean by that? Let's say I have an input. Now that input, we should not change directly to 1, 1. So if we are changing directly to 1, 1, we are changing both of the inputs at the same time, but we don't know exactly what time is that going to change. Okay, so rather than doing that, we can do it like 0, 0, then 0, 1. So we are changing one at a time, wait for a stable one, and then we can change the other one. Okay, like the gray codes. And then we can change it this way around. And we keep the other one stable and we change the other one. Okay, so instead of having a simultaneous change of two or more variables, we just do it once at a time, like the gray codes. So another important thing is the fundamental mode of operation. So what is this fundamental mode of operation? Now, this means that the input signals can change one at a time and when the circuit is in stable condition. So this is one thing that we need to satisfy. Inputs change one at a time and when the circuit is in stable state condition. So that means the present state matches to the next state. Okay, so these are the two fundamental mode of operations that we need to consider. Okay, now one thing that we need to be careful with the asynchronous and the synchronous. Now, asynchronous circuits, the internal state can change immediately after a change in the input. But the synchronous one, present state specified by the flip-flop values and does not change if the input changes while the clock pulse is inactive. So these are the two important differences between asynchronous and synchronous. All right, let's do the first example and let's try to analyze a sequential circuit without clocks, which is an asynchronous sequential circuit. Okay, so we have got next state y1, present state y1, next state y2, present state y2, and input x, and some combinational logic here. So let's derive the first equations and find out what will be these equations. So let's start with y1. Now, what is next state equation for y1? So y1 is actually small y1 and x. So present state y1 and x, or it is x prime and y2. X prime and y2. This is y1. Then let's find out y2 as well, which is going to be, this is x and y1 prime and x, or, and also this is common, which is x prime y2. So now we have got two equations, next state equations for our circuitry. Now, what we do is, in this type of designs, we do the analysis. In analysis, we actually generate transition tables. So the first step is transition table. Now, this transition table, it looks like a K-map, but it is not actually, because in transition tables, we have got the next states, y1, y2. We have got x on top, and present states y1, y2 on the side. And this part is similar to K-map. So when x is 0, when x is 1, and we have got four possibilities, like the gray code, 0, 0, 0, 1, 1, 1, 1, 0. So that's our transition table. You can also create a state table. It's similar to what we have done in chapter 5. But transition tables are more important. Now, when we look at it, all we need to do is we just need to put these in. So y1, for example. So y1 is 1, where x is 1 and y1 is 1. So x is 1, y1 is 1 at these 2 points. So that means these are going to be 1s. Or x is 0 and y2 is 1. So x is 0 and y2 is 1 on those 2 points. And the rest for y1, they are just going to be zeros. y2, now it's y1 prime and x. So x is going to be 1 and y1 prime. So those 2 points. So we put 1 on those. And x prime, y2. So x prime, y2. y2 is going to be 1 on those points. So x prime, y2 is those 2. And the rest are just zeros. So we have got the transition table. Now, next thing that we look at in the transition table is which ones are going to be stable states. So what do we know about stable state? Small y, k, must be equal to capital YK. The present state must match to the next state. So these are all our next states, and these are all present states. So which ones are matching? Then we have to circle those. So when present is 0, 0, next is 0, 0, this is stable. When present is 0, 1, next is 0, 1, this is stable. Where x is 1. And present is 1, next is present is 1, 1, next is 1, 1. This one is stable. And present is 1, 0, next is 1, 0. This one is stable. So we can easily show which ones are the stable states and which ones are not. Now, what we can say is stable states are going to be, so y1, y2, x case, and it's going to be 0, 0, 0 condition. Then it's going to be 0, 1, 1. So the present states and the input, or 1, 1, 0 and 1, 0, 1. So these are the stable states. And then we also have unstable states, which we can also write them down. The rest are unstable. So again, y1, y2, x. So 0, 0, 1, so 0, 0, 1. And then 0, 1, 0. Sorry, that's 0, 0, 0. This is 0, 0, 0. Then 0, 1, 0. And then we have got 1, 1, 1. And 1, 0, 0. And these are all our unstable states. So this is how we do the analysis related with these equations of the asynchronous sequential circuit. One another thing that we can do as an analysis is the flow table. So flow table, once you derive the transition table, drawing a flow table is quite easy. We are just assigning the variables to these states, and that's it. So let's say y that's x 0, 1, and states small y, so a, b, c, and d. So in this case, we can say 0, 0 is a, 0, 1 is b, 1, 1 is c, 0, 1 is again b, c, d, a, and d. And again, we can assign, circle the ones which are stable. And that was representing our primitive flow table, which shows a flow table actually. The primitive one, it shows one stable state in each row, which we have it in this case. Okay, so this was the first example. Let's do another one, just to make sure that we understand. But this time, the flow table will be given. So state table similar to chapter 5, as I already mentioned. Stable states and unstable states, as we all mentioned it. And we just circle the ones which represents the stable ones. And the primitive flow table is what we have drawn over here. Okay, so next example. Now we have got two inputs and one feedback path, which is y. So that means this will provide us two states, A and B, and state assignments are given. So A is 0, B is 1, and one output annotated with the state, as you can see, which is written next to the states. So these are the outputs. Okay, so in order to analyze it, the first thing to do is, again, the flow table is given. We can derive the transition table. So transition table for this flow table is, what we need to do is, we can write this as numbers rather than the letters. So This is x1, x2, and y, a, b. So 0, 0, 0, 1, 1, 1, 1, 0. Now these are the present states and the next state. So this one is going to be just 0 and 1 because we are keeping the letters out now. We have got the numbers. Okay, so if we start with the first one, 0, 0, 0 over here, it's A. So we can say it's 0, then 0, 0, and then 1. So 0, 0, and 1. And B is 0, 0, 1, 1. So 0, 0, 1, 1. Letter A is 0, letter B is 1. For the outputs, we can actually create a separate table. You can say output table. Again, it's similar. I'm just putting them in separate tables so that analysis will be easier. X1, X2, and Y. So 0 and 1, 0, 0, 0, 1, 1, 1, and 1, 0. So the output table, we just need to put down whatever we have got as an output, 0, 0, 0 for the first row, and 0, 0, 1, 0 for the second row. And that's our outputs. Now, so how can we derive an expression from these? It's so simple. We just need to apply the K-map techniques here. So first, if you want, we can identify which ones are stable. So this is stable, this is stable, this is stable. Why? Because the present is equals to the next. And when y is 1, these two are stable because present is equals to next. Okay. Now, how do we write an expression for it in order to derive the logic gate from it? Now, if I take this and combine these two, so y is going to be x1, x2 prime, or these two can be combined, which is x1, y. So this is our expression for the next state. And for the output, it's just 1 over there. So z is x1, x2, y. Now we have got the expressions. All we just need to do is drawing it. So two AND gates, one OR gate, and we have got x1, x2 is inverted, and also x1 going down here, and y. So y is coming from here as a feedback, and these are connected. And output is just combination of x1, x2, and y. So we can just have an AND gate over here, which will represent z. So x1, x2, and y. And this will give us the z. And this is small y. So that's how we can derive from flow table to the circuit. In the first example, we have seen from the circuit to the flow table. And the second example, we have seen flow table to the circuit. So we can easily analyze and find out the asynchronous sequential circuits.